A dynamical system moves through a state space one step at a time. Each realization is a single path, one possible history of the system. Some states are absorbing. Once the system enters an absorbing state, it can never leave. Survival means the path has not yet reached that state. Expectation averages across all paths simultaneously, including the ones that were absorbed. The stopping time is the first moment the path crosses the terminal boundary. If the path never crosses, the stopping time is infinite. Survival is exactly the event that the stopping time is infinite. Expected value at a fixed moment is an average across all paths at that moment. Absorbed paths still contribute to that average. Survival and expectation are defined on different mathematical objects. They are not equivalent. Three quantities arise naturally from a stochastic process. First, the expected value at a fixed time, an average over all paths. Second, the probability of surviving to that time, the fraction of paths not yet absorbed. Third, the almost sure limit, what the path approaches as time grows without bound. None of these three quantities determines the others. A model that treats them as equivalent will produce structurally wrong predictions. A high expected value does not constrain the survival probability. Rare but large positive outcomes can hold the ensemble average high while the majority of individual paths reach the absorbing barrier. Expectation is an averaging operator. It is not a constraint on what any individual path does. A model optimized for expected return does not control for ruin. In a fair random walk with an absorbing barrier at zero, the expected wealth stays constant at its starting value. Yet every path is eventually absorbed. Ruin is certain over an infinite horizon. The expectation looks stable. The path collapses. Constant expectation and certain ruin are not contradictory. They operate on different objects. In a branching process where each individual produces on average exactly one offspring, the expected population size stays constant at its starting value. Yet extinction occurs with probability 1 whenever offspring count varies at all. The expectation follows one trajectory. The process follows another. Only when there is zero variance do the two objects agree. Variance creates the gap between them.